distribution, right? When you see that word or those two words, you should be thinking of a bell curve. Okay, and by that specifically, I want you to think of if you were to graph occurrences over, the x-axis, you would have a bell curve which is symmetric, right? Human characteristics, not just humans, but also in nature, right? We observe that such as height, weight, intelligence, right? The IQ scores, etc. produce data or data, right? That is normally distributed. Okay, and again, I will do this again. So if you just focus on the x-axis, right, you always want to focus the mean as the location, right? The average is the location of the highest point of the curve. That's where most data points will cluster around. So I always go from that mean, I go down to the left, and then I go back to my mean, and I kind of go down to the right, and make it as symmetric as possible, right? Examples in nature, right, would be hatching of birds in the spring, right? There's this, like most geese or whatever, right? They will lay their eggs at a certain time, like all a bit scattered, but most of them are being laid at the same time, or they will hatch kind of at the same time, but there's some that hatch a lot earlier and some that hatch a lot later, but there's this average date where most of them will hatch, right? Migration of birds or other animals, doesn't just have to be birds, right? There's an average date, right? So that it kind of all goes by that, right? So here we have a graph. So if you have a ruler, this is where you want to make sure you have it. So you have your y-axis, right? That is what we refer to as the frequency, how often it happens, right? And you have your x-axis, so this is your data, and that data can be, so frequency up the y, data here, and data could be in kilograms, it could be in meters, feet, days, hours, you name it, right? So whatever you're considering, right, that's our data. And then we figure out how often does the data fit in each category. Okay. Now, let me count here. 1, 2, 3, 4, 5, 6. I need you to have 9 marks along the x-axis. So I'm going to set my ruler. I'm going to use the centimeters for it. So I'm going to go 1, 2, 3, 4, 5. And I have lots of room here in mine. So I'm going to keep going a little bit. I'm going to go 10, 11, 12. So I have 12 markings along the x-axis. Try to make that happen. At some point along the x-axis, we have what we call our average. Like that's where most of the data is going to be clustered around. So I'm going to count from this end. If you have 12 marks, I was just going to double check because I want you to have the same as me. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you have 12 marks, I want you to start from this end, from the very, like on the right side here. So you go back 1, 2, 3, 4. We're going to make this our average in this case. So you put that average there. And as we go to the left, we're going to say that this mark here represents minus 1 standard deviation. This is going to be minus 2 standard deviations, minus 3 standard deviations, and minus 4 standard deviations. We're going to stop at 4 because after that it gets really, really small. To the right, you go plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations, and then plus 4 standard deviations. And if you need to add more marks to make this work, you do it, right? Okay, so I want you to now go to the average and just go a little higher up here. Right about there is fine. It's about halfway the height of my frequency, right? And then we're going to try to make our curve, but never touching. You never touch the x-axis. Remember that from the video? Okay. And then you go to the right and do the same thing. Try to make it, should look like a bell. Okay. I know it's kind of difficult to make this graph. That's why I'm trying to give you specifics. Now you need your ruler again. We'll make more of these, by the way, so don't panic if you're not getting it exactly right. So I'm going to actually partition, right? The mean is right here. And I'm going to go to every single mark and just go up to the top until you hit the bell curve. What was that rule again? Do you remember? There's 3 numbers. Anybody remember the 68, 95, 97.5 rule? Yeah. So what we know when data is normally distributed like this, Okay, we know that if you were to take like one standard deviation to the left, you start there, and you were to go to the standard deviation that is to the right, so one to the left, one to the right, I'm going to do this outside the curve, right? We know that that percentage of plus and minus one standard deviation is 68%. Okay, 68. So basically 34% here and 34% there. Okay. We also know that if you were to take two standard deviations, so I'm kind of just following the -2 here and making a line up there. Okay, I know that that is plus or minus 2 standard deviations, which amounts to 95% of the data. 95% of people, birds, you name it, right? Instances are going to fall within 2 standard deviations away from the, so that would make this 13.5, by the way. These percentages are very important. So if your graph looks terrible, but you have the percentages, that's right now what I want you to focus on. And maybe I will zoom in a little bit here. Okay, so 13.5 and 13.5, that adds up to 27, plus 68, that is 95, right? If you were to add up all these 4 sections, that adds up to the 95. And then we go out one more, and I'll just tell you that this should be 2.35%. Did you hear that? You can hear me say that, right? 2.35 if you're not sure, right? So if you go to the top, you take that, the right side of the third standard deviation and the left side, you now know that if you were to go 3 standard deviations to the right and to the left, you would have 99.7%. Oh, you can't see that. There we go. 99.7%. So this little sliver here, I will just maybe do with an arrow. That is 0.15%. And this little sliver here is 0.15%. So basically 100% of the data would fall within 4 standard deviations of the mean. So here's a big one that I want you to add, because if your mean is like 1,000, or let's say it's 10,000 kilometers or whatever, to be this close to your y-axis is actually wrong, right? So to cheat a little bit, or to help us out, we use this tool, right? We use a zipper. That's just my term, right? If we skip values along x-axis. So I want you to use a zipper. That way you don't have to like start from 0, 100, 200, all the way to 1,000. You can just go from 0 straight to 10,000 if you want to. You're kind of skipping some values there. So this is just like a little cloud. There we go. And note that percentages in each section represent represents the likelihood of data falling in that category. I will also add this. If data is normally distributed, it follows the 68, 95, 99.7 rule. A large standard deviation will result in a flatter curve. A small standard deviation will result in a sharper curve. Oops. I need to zoom out a bit here. The last point I want to add, total area under the curve is 100% or 1. So the percentages are also like probabilities, okay? Can we add that to the first point here, the first bullet? I will just do this. Likelihood is equal to probability. Because sometimes they will say, what's the probability that, you know, someone will have studied between 5 and 10 hours, right? And so it is the likelihood, the probability of that happening. So an example now. So we're going to practice how to draw this curve quite a bit. And we will often refrain from graphing the y-axis. We're just going to focus on the x-axis, but I want you to know that there is a y-axis to be considered. Okay, example. The height of people in Canada is found to be normally distributed. The mean height is 177 centimeters with a standard deviation of 2.5. And this could vary, right? The numbers can have decimals, you name it. But the standard deviation, when you calculate it, so imagine they've kept track of all a bunch of people, right? They just kept track of their heights. They entered into the TI-84. Not really. They use other computers or whatever. And then it spits out that the average is 177 and the standard deviation is 2.5 centimeters. Okay, so we're going to do this step by step. So A, graph a normal curve, labeling, comma, labeling, plus or minus 4 standard deviations from the mean. So you always want to leave, I don't know, 2 or 3 fingers. If it's my finger, it's probably 2. If it's your finger, it's probably 3 or 4. Right? My fingers are a lot bigger. So you want to leave yourself some room and just make a straight line like this. Okay. That's going to be the x-axis, so to speak. And we're talking height. That's what we're collecting. And that height is in centimeters. So you got to make sure you have that written down. And somewhere in the middle, it's okay to just kind of guess where it is. But you're gonna make a mark in the middle. That's your average. That's where you want the 177 to be. And then you go 4 to the right and 4 to the left from that. Okay? So whatever you can do, so I'm going to go 1, 2, 3, 4. Stop there. And I'm going to go 1, 2, 3, 4 to the left. And so this is my average, which is 177. We know that it's in centimeters. I don't need to write the units down because I've done that already. Okay. We know that here I'll have 1 standard deviation. This will be plus 2 standard deviations, plus 3, plus 4. So to the right you add, to the left you will subtract. And then you grab your calculator. I mean, you can do mental math, that's fine. But sometimes you will make a mistake and then everything is off, especially if you don't recognize that number that I'm asking for. So you go 177 plus the standard deviation is 2.5. So you add 1 standard deviation to get you to 179.5. You keep adding a standard deviation to get to the next one, and so forth. Right? So all the way to the 4th standard deviation is 187. How could you have done this faster? You could have gone 177 plus 4 standard deviations. So 177 plus 4 times 2.5, that's what this is saying. You would still get 187, right? Like it's up to you, but basically from one to the other, you're increasing it by 2.5 every time. Because that is our standard deviation. That's the standard value by which we go up along the x-axis. Okay, and so you do the same thing going to the left now. You go 177 minus 2.5. Right, so this is 174.5. Right, minus 2.5 again, that's 172. minus 2.5 again, that's 169.5. Minus 2.5, that's 167. And so basically what happened, and you don't need to do the arrow thing every time, okay? That's just for your notes. Okay, so you have 4 to either side and you're done there. Then you go to your mean, you go and find the highest point that you can possibly get, make a little dot there, then go make a bell. As best as you can. I'm not gonna pick it apart, but if it doesn't look symmetric at all, that's when you might get in trouble. And so these percentages should be on your study sheet. Okay, so 34%, 34%, 13.5%, 13.5%. If you don't remember them, you need to write them down, right? 2.35%, 2.35%, 0.15, 0.15. Done. That's all you need to do. You also need to remember when you're looking at this, these are the heights of Canadian citizens. So there's a 68% chance, right? 68% chance that someone will be between 174.5 centimeters and 179.5 centimeters, right? That's what you're determining here. That's the likelihood. Basically, when they make shoe sizes, shirt sizes, anything like that, they kind of go by this, right? Which one are they going to make more of? Whatever falls to the left and to the right of the average size, right? That's within what they're going to make, right? So A. Oh, sorry, B. This is B. What percentage of the population has a height between 172 centimeters and 179.5? Question mark. By the way, if you make this graph, use your graph. Why am I saying this? Because some of you will be tempted later on when I show you the shortcut to use your calculators. I want you to use that graph, okay? And I will probably say that anyways on the question, but just to let you know. So between 172 and 179.5, I start 172 here, and I will go all the way to 179.5, right? So from here to here. So 172 is right here, so I need to go 13.5% plus 34% plus another 34%, right? And that gets me there. Like if I add up these three sections, that gets me between 172 and 179.5. Okay, so that will be a total of 81.5% of the population. We don't know how many people, but we know that 81.5% of whatever, sample size you take will fall in that category. So you know how I tell you never to make the line touch the x-axis, right? What's the tallest? The tallest this one accounts for is 187 centimeters. You know what my height is? 192. 6'5", right? So Am I on this curve? No, I don't, right? So technically there's always a chance somebody is out there, right? Like I'm out there, don't forget about me kind of thing, right? So don't make the line touch the x-axis, right? Because there's always a chance somebody's outside that line, okay? So C, I'm just doing that to make you remember, right? Whatever I can do to make you remember that. What percentage of the population will be taller than 182 centimeters? So let me go back up to the graph. You would all have to agree that the further to the right you are, the taller you are, right? And the further left you are, in this case, you'd be shorter. Okay? So taller and shorter. So what percent of the population would be taller than 182 centimeters? 182 centimeters is right there. So it would be these sections right here that would give you that number, right? 2.35 and 0.15. 2.35 plus 0.15, which is 2.5%. Okay, D, percentage of people shorter than 182 centimeters. Two ways of doing that. A lot of them are, you have two ways of actually calculating that. The whole bell curve represents 100%. I will take away the 2.5% that are taller than that, which leaves you with 97.5% of people. Did that make sense what I just did there? I took away the ones that are taller, leaving me with the ones that are shorter. What would have been an alternative to that? Well, you go up and this is your 182, right? You just add up all of these sections and you get there too. It's the same thing. It's just, this is a quicker way of doing that, right? E, range of heights. And you got to remember, range is high minus low. The highest number on my graph is 187 centimeters. And the lowest, if you look, is 167. So that's 20 centimeters is the range of heights that this graph will account for. Doesn't account for me, but anyways, most people, right? 99.7% of people would be taken care of. Okay. This is a more challenging, and I kind of ran out of runway here, but we'll make it work, okay? Just be conservative with your space there. If Canada's population is 35 million, comma, how many people are shorter than 174.5 centimeter. Question. Well, shorter than 174, let's go look it up. You go to your table, to your graph. I will do the same. So just hang on there if you're still copying. Shorter than 174 means that I have to add up the percentages to the left. So I'm going to add up probability. It would be 0.15 plus 2.35 plus 13.5%. And so that gives me 16% chance that somebody's going to be shorter than 174.5 centimeters. Does that answer the question though? They want to know number of people, right? So we will say this. People would be probability times total. And here's where I'm running out of room here, sorry. So it's 0.16 times 35 million. So I turn that 16% into a decimal because you cannot multiply percentages times anything. You got to turn that into a decimal. You divide it by 100. And so I go 0.16 times 35 million. And that gets you to 5,600,000. Where am I going to fit that? I'm going to do a unconventional here. 5,600,000 people. Can you see that? It's like a choo-choo train there. Yeah. So this question, I will give it away. Okay, this is a freebie. Will be worth 2 marks. So if you do a graph like that, everything is 1 mark except for that one is 2 marks. So you know, okay, I need to do some more work here. I need to find out the percentages and then multiply it by whatever we're talking about. It could be cans produced by, by a pop company that makes pop drinks, right? Whatever. This applies to so many different scenarios. Okay. Okay. Where are we at? Okay. What else did I want to say about this? Can you go back to the first graph we did here? I can see that I probably didn't leave enough room. So I will leave this for today. I was trying to see if I could do 2 and 1 here, but there's something called z-scores. Okay, this is not a German person trying to say the scores, it's z-scores. Okay, so the z-scores tell you how many standard deviations away you are from the mean. So we're not going to do that here because it's going to get too messy there. I thought I was going to try it, but I looked at some of your notes and it's too close, too close. Okay, so homework. Page 251 in the textbook. Question 1, 10, 11, 13, and 14. And I will say this because the question doesn't do that. Sketch normal curve, comma, then answer questions. So I want you to do that because it's actually pretty easy to do once you have done a couple. Okay. So given that I told you don't bring your textbooks, right? I will just put it up here and you can get started on that. 251. Question 1, I will have 1 up there. So try to do question 1 right now, and the rest I will move it up in a bit, but for now just do these ones. Oh, that letter mu, that's gonna, do you remember what mu stands for? It's actually average. Okay, so don't let that throw you off. I'm not gonna be too picky about it. I'm usually gonna go X bar, but the textbook does use mu. Okay, that letter. It's almost like a U with a little extension. Don't worry about it too much.